Hello viewers, today I am going to discuss the water requirement of crops and factors affecting it. Water is required by the crop to meet its evapotranspiration demand as well as for metabolic activities of the plant. The determination of water for the plants is necessary for judicious use of limited water available. Therefore, water requirement is needed. Water requirement vary from crop to crop and area to area depending upon the soil types. Even water requirement is affected by climatic conditions as well as management practices. So, all these things will be covered in this lecture. Water requirement is the quantity of water needed for normal crop growth and yield that may be supplied entirely by precipitation or irrigation or by both. Water is needed mainly to meet the demands of evaporation, transpiration and metabolic needs of the plants, collectively known as consumptive use. Cu is equal to E plus T plus metabolic needs, where E represents evaporation, T represents transpiration and the next is metabolic needs. The amount of water consumed in plant metabolism is very small, less than 1%. Cu and Et are considered more or less equal. It is always not possible to exactly apply the required quantity of water to bring the root zone to field capacity. Some losses, that is percolation, runoff, seepage, etc., are unavoidable. They are known as application losses. Water is also needed for special purposes like leaching of excess salts, land preparation, pre-sowing irrigation, etc. These are collectively known as water for special operations. Water requirement therefore include all these components. Water requirement is equal to evapotranspiration plus application losses plus water for special operations. In this way, when there is more application efficiency, definitely less water will be required. Similarly, when there is less water is required in special purposes, then ultimately the quantity of water will be reduced. Water requirement of crops can also be expressed in terms of source of water. Water requirement is equal to irrigation water plus effective rainfall plus water contribution from the soil profile. In this case, IR represents irrigation requirement, ER represents effective rainfall and S represents soil profile moisture contribution as stored soil moisture or shallow groundwater table. Sometimes there is shallow water tables and under those conditions there is contribution of water from the groundwater, and in this way due to the groundwater contribution ultimately water addition through irrigation or water added through the precipitation, that requirement is greatly reduced. Irrigation requirement is the total amount of water applied to a cropped field for supplementing rainfall and soil profile contribution to meet crop water needs for optimum growth and yield. Irrigation requirement is only a part of water requirement, and the irrigation water requirement may be expressed as IR is equal to WR minus ER plus S. Here IR is irrigation requirement, WR is water requirement, and water requirement minus effective rainfall plus contribution from the soil profile. Net irrigation requirement. Net irrigation water requirement is the amount of water exclusive of precipitation and profile soil moisture contribution required for optimum crop production. In other words, it is the amount of irrigation water that must be stored in the root zone to meet the consumptive use requirement of the crop. Gross irrigation requirement. Gross irrigation requirement is the net irrigation requirement and losses in conveyance, distribution and application of water in operating the system. Therefore, gross water is generally computed and the water is applied to the field as per gross water requirement, so that the net water availability will be there in the root zone depth and ultimately the plant will not suffer from paucity of water. Effective rainfall. All the rain received in a single occasion may not be entirely useful for crop. Part of it may be lost as surface runoff, deep percolation beyond root zone or by evaporation of rain intercepted by foliage. The extent of its utility in a given region determines effectiveness of rainfall or rainfall efficiency. Effective rainfall is that fraction of the total rainfall available for the consumptive use of the crop. So, the total rainfall is not being utilized by the plants. Say for example, if there is rainfall just after irrigation, then almost all the rain is not effective for the plant purposes. But when there is a deficiency of water in the soil profile, that is the root zone depth, in that case most of the rainfall is being absorbed by the root zone depth and that is effective. When the excess rainfall is there, then some of the water percolates beyond root zone and that comes under ineffective rainfall. Factors affecting crop water requirement. The factors can be divided into 4 groups, that is crop factors, soil factors, climatic factors and management practices. Crop factors. Water requirement vary from crop to crop. Say for example, the requirement of water for wheat is different than that of barley. The requirement of water is different for mustard and chickpea. In case of wheat, the water requirement is almost 500 millimeter, whereas in case of barley, the requirement of water is about 380 millimeter. In case of mustard, it is 350 millimeter, whereas in case of chickpea, it is 280 millimeter. So, there is difference in requirement of water from crop to crop. Differences in duration, rooting characteristics and canopy structure of the varieties within the crop influence the water requirements. Again, I will like to quote the example. In case of wheat, variety Raj 3077 has less water requirement in comparison to variety PBW 343. So, this is due to the difference in yield potential of a particular variety, due to difference in growing period of the variety. So, because of these differences, the water requirement even differ from variety to variety. Longer the crop duration, higher will be the water requirement. In general, deep rooted crops extract more water from deeper soil layers. High leaf area increase evapotranspiration. Tall crops intercept more solar radiation and have more evapotranspiration than short crops. Soil factors. Evaporation from soil surface depends on hydraulic conductivity, reflectivity and thermal properties of the soil. Coarse textured soils have higher hydraulic conductivity than fine textured soils at high soil moisture regime. Hence, the evaporation is higher from coarse textured soils. Higher proportion of aggregates of more than 1.0 millimeter diameter reduce upward water movement and hence evaporation. ridges and furrows minimize evaporation losses. Dark colored soils absorb more heat, leading to higher rate of evaporation from the surface. Because of this reason, in case of sandy soils, more irrigations are required, more frequent irrigations are required in comparison to medium textured and heavy textured soils. Simultaneously, water loss is also more in coarse textured soils in comparison to medium textured soils and heavy textured soils. Hence, the water requirement differ under these two conditions. Climatic factors: solar radiation, temperature, relative humidity and wind velocity have strong influence on evapotranspiration. High temperature, wind velocity and solar radiation increase the crop water needs. High humidity reduces the evapotranspiration. Hot and dry winds around the irrigated crop, that is advection, increase the evapotranspiration. Advection is important in arid regions. In Rajasthan, where the atmospheric temperature is quite higher, under these conditions advection is very important factor, and shelter belts are required for good crop production under these conditions and to minimize advection effect. Similarly, in arid and semi-arid conditions, water requirement increases due to low humidity under these climatic conditions. To maintain humidity, irrigation is required. Management practices: any crop management practice aimed at improving the crop growth and yield increases the crop water requirement. Timely weeding reduces competition for moisture and mulching reduces evapotranspiration, thus minimize evapotranspiration. Frequent irrigations result in higher proportion of evaporation and considerably increase the crop water needs. So, the management practices are very important. In some of the crops which are deep rooted, the first irrigation is generally delayed, because when the first irrigation will be delayed, then the roots will penetrate deeper and root will take water from the more soil volume, and ultimately the irrigations will be reduced. Similarly, when mulch is added on the soil surface, then evaporation is reduced and ultimately the water loss will be reduced. Similarly, when the intercultivation is done, then weed control is there, and because of the weed control, the wastage of water will be less. Moreover, when there is a pulverization of the soil and breakdown of the capillary, then again evaporation will be reduced. So, these management practice have profound effect on requirement of the water to the crops. Methods for determination of crop water requirements. Methods for estimating crop water requirements depend on the desired level of accuracy, availability of equipment and technical know-how. Some of the methods for determining crop water requirements are transpiration ratio method, depth interval yield approach, soil moisture depletion studies, field experimentation, climatological approaches, drum culture technique for lowland rice and water balance method. So, adoption of these methods depend on the requirement of data, how accurate data are required, what technical know-how is there for determination of water requirement. Transpiration ratio method. The amount of water transpired by a crop to produce a unit quantity of dry matter is called transpiration ratio. In spite of several drawbacks, it was the usual method in earlier days. Transpiration ratio measured in greenhouse with pot culture studies differ under actual conditions. hence it is of little value for scheduling irrigation. This is the easy method, but as far as scientific background is there, that is less in this method, and there is always difference in water requirement under pot conditions and under field conditions. So, the accuracy in this method is less in comparison to other methods. Depth interval yield approach. Irrigations are scheduled with different depths of water at different intervals between irrigations. Total amount of water used for highest yield is taken as crop water requirement. It gives an idea on crop water needs, but not reliable estimate because of differences in climate in different seasons. As we know that the climate differs from season to season. Sometimes there is more temperature in the same season, sometimes there is less temperature in the more season. Sometimes there is frequent rainfall, sometimes there is less frequent rainfall. So, the climatic conditions will vary from season to season, and on the basis of one season, one cannot take accurate values of water requirement. So, definitely there is this drawback in this method of determination of water requirement. Soil moisture depletion studies. Consumptive use of water can be determined by estimating changes in soil moisture from root zone depth at periodical intervals during the crop season. It is usually employed in fairly uniform soils where the groundwater table is deeper enough to influence soil moisture in the root zone depth. This can be depicted in the form of formula Cu is equal to summation of M1i minus M2i divided by 100 multiplied by bulk density of ith layer and depth of the ith layer. Here Cu is consumptive use from root zone between two successive sampling periods in millimeter, and is number of soil layers considered in root zone depth d. M1i is soil moisture percentage at first sampling in ith layer. M2i is soil moisture percentage at second sampling in the ith layer. BDI is bulk density of the ith soil layer in grams per cubic centimeter, and Di is depth of ith soil layer in centimeter. By using this formula, the water from sowing to harvesting of a crop can be determined. Effective rainfall, groundwater contribution and deep percolation losses, if any, are to be considered for reliable estimates of crop water requirement. Seasonal consumptive use can be obtained by adding consumptive use values of each sampling interval. In this way, this consumptive use of each seasonal values and effective rainfall plus deep percolation losses, all these factors are taken into consideration for determination of water requirement of the crop. Field experimentation. Crops are grown with recommended management practices, including an ideal irrigation schedule for optimum yields. Irrigation water applied, effective rainfall and soil profile moisture contributions are measured. Seasonal water requirements are computed by adding these components. WR is equal to IR plus ER plus summation of MBI minus MEI upon 100 multiplied by BDI multiplied by DI, where WR is water requirement of crop in millimeter, IR is amount of irrigation water applied in millimeter, ER is effective rainfall during the season in millimeter, N is number of soil layers considered in the root zone depth D, MBI is soil moisture percentage at the start of season in the ith layer. MEI is soil moisture percentage at the end of season in the ith layer. BDI is soil bulk density in the ith layer, and DI is depth of the ith layer in root zone depth. Soil moisture depletion studies and field experimentation. These are accurate methods of determination of water requirement of the crops. However, these methods take more time and there is more accuracy in these methods. Climatological approaches. Climate largely determines the evapotranspiration. Empirical formulae for its estimation have been developed. Water requirements can be obtained by adding application losses and water needed for special operations to the estimated evapotranspiration of the crop. So, this is the another approach which is being used for determination of water requirement of the crops, and here computation is needed and the climatological parameters are required for determination of water requirement by climatological approaches. Drum culture technique for lowland rice. The determination of water requirement for aeration crops is different than rice. Here particularly for rice, the determination of water requirement is done by drum culture technique. Components of water losses in lowland rice fields, that is percolation, evaporation, transpiration and ineffective rainfall, can be measured by drum culture technique. 4 metallic drums of 50 centimeter by 50 centimeter diameter having height of 120 centimeter, 2 with bottoms and the other 2 without bottoms, are embedded in the rice field leaving 20 centimeter above the soil surface. Placement of the 2 drums with bottoms, that is A and B, can be by excavating the soil layer wise and filling the drums with the excavated soil in the same sequence. Drums without bottom, that is C and D, can be embedded by excavating the soil outside the drums. Rice seedling are transplanted in the drums A, C and D along with the field surrounding the drums. Rice seedling are also transplanted in drum B along with other 3 drums, however without root system. Rooting plants are replaced every week with plants of same age and size from bulk crop surrounding the drums with roots cut off. These rootless plants in drum B shade the soil age plants in the other 3 drums. Water level in the field and drums should be the same. Water level in the drums is measured every day and losses due to percolation and ET are replaced. Excess rainfall, that is ineffective rainfall, if any, then is desired to be maintained, can be collected in a jar with mouth closed and buried in the field and connected to drum D. So, the different components can be estimated by this technique, and here percolation will be difference in water depth between drums C and A. Evaporation will be daily loss in drum B. Evapotranspiration daily loss in drum A. Transpiration difference in water depth between drum A and B. Effective rainfall, total rainfall received minus ineffective rainfall collected in jar from drum D. The graphical depiction of these 4 drums has been shown in this figure, and the drum A and B are having bottom where C and D are not having bottom. The ineffective rainfall is collected in jar which is attached with drum D, and the drum B is having plants of the same age but without roots. So, these plants of the same age without roots will check the evaporation losses. So, here drum A will represent here evapotranspiration, drum B will represent the evaporation, whereas the effective rainfall will be computed by drum D. The another method of determination of water requirement is water balance method. Evapotranspiration from a large area like a watershed can be estimated by water balance method. It is the estimation of incoming and outgoing water from an area. Water is added to the soil by precipitation, irrigation and groundwater contribution. The different losses were evaporation, transpiration, deep percolation and surface runoff. P plus I plus S is equal to E plus T plus D plus R. So, here the components of incoming water and the component of loss of water are equilibrated, and on the basis of this irrigation requirement can be determined. Evapotranspiration can be estimated by measuring precipitation, irrigation water, deep percolation, surface runoff and groundwater contribution. Here in this figure, all the components of water balance have been shown. Here the components of water addition, that is precipitation, irrigation and profile contribution has been shown, as well as the components of water loss, that is evaporation, transpiration, runoff and deep percolation losses have been shown in this figure. So, the water requirement by computing other components of water balance can be determined by water balance method. In this part of the program, I have discussed the crop water requirement of crops and factors affecting it. Determination of water requirement is necessary for judicious use of limited water. Various factors are responsible for affecting water requirement, and these factors are soil factors, crop factors, climatic factors and management practices. By knowing these factors, we can manage the limited resources of water, and judicious water of this limited natural resource may be done.